Thank you. Yeah, I'm really into synthwave and retro stuff. Yeah. Yeah, I'm always looking for cyberpunk wallpapers. All right, 5 more minutes. No one else has joined, so I think we can just start right now. And also, I see that there's like a 40-minute time limit on the Zoom meeting, so I don't think we should wait too long to start. So I'll start right now. So click on the link that I sent in the chat, and if you don't have experience with Colab before, well, unmute yourself or send a message in the chat if you don't have experience with Colab. Otherwise, I'll assume that you do. Okay. All right, so just create a copy of this Colab. As a reminder to do that, just go to File and click Save a Copy in Drive. All right. After you save a copy of this notebook. I'm not sure if this is available for all Colab users, but if you go under runtime, I would just give this a try. Go under the runtime tab and go all the way down to change runtime type. It's the third option from the bottom. Change runtime type, select that. And once we get to training our neural network, it will take extremely long if these aren't selected. So if you can, select GPU for your hardware accelerator. By default, it's most likely none. So select GPU, and your GPU class, select premium. Well, I think you can select GPU on all plans, and then you can select standard. So select standard or whatever. And then if there's an option, select high RAM or click select standard. But as long as you select GPU, you should be fine. And then click save. And then we can start. So, as you know, this meeting is going to be about natural language processing, or generating text with RNNs. It's kind of like auto completion, basically, in a sense. And RNNs, well, RNN stands for a recurrent neural network. And when someone thinks about a neural network, or when someone says a neural network, and if you have computer science experience, you probably think of a network like the one on screen here. You have your input layer, and then you have all your hidden layers, and then an output layer. Or you might think of a convolutional neural network if you're really into image processing or things like that. And right here, it's really just the simplified presentation is just condensing it down. You have your input layer where your input is taken, and then the hidden layers, which have those weights and biases that change the values. Then it comes all the way out to the output layer, and then you get your final predicted output. And this conventional neural network is called a feed-forward neural network. A recurrent neural network builds on top of the concepts from a conventional neural network, in that it remembers data. We will explore a variety of recurrent neural networks capable of LSTM, which is long short-term memory. LSTM is essential to many problems that are solved in machine learning today, and it enables neural networks to process not just single data points, but also entire sequences of data. It allows it to process sequential data, and later on, we're going to go to some scenarios in the scenario example section. You'll get an example of a scenario, and you'll guess if it's an RNN or a feed-forward neural network, and which would work best for that. And then you'll get the answer. So in the diagram below, X, H, and Y represent different layers in an RNN. So X is parallel to the input layer, kind of, that we see up here in the simplified presentation of just a feed-forward neural network. H is like the hidden layer, and Y is like the output layer. So, and notice that there's only one hidden layer, which is H. So while feed-forward neural networks have multiple hidden layers, each with multiple nodes, RNNs have a single hidden layer, still with multiple nodes, that data is repeatedly fed into. This repetition becomes helpful in recalling previous inputs and outputs to into the hidden layer. So it can refer back to inputs that were added to it before, and it sort of keeps track of this inside of it. And we're going to see some scenarios right here below. And I believe later in the code, you kind of get to see more closely what we're doing with that. But you can see right here that it's kind of like, say you're on the hidden layer, you can go back to previous states and see where what was previously fed into the neural network and what the output was And that way you can process data that's sort of occurring over time. So here's some scenarios so you can sort of get an idea of what this would necessarily be used for, because for me, it didn't come to mind immediately what RNNs would be used for, and why RNNs are important compared to feed-forward neural networks. So so here's some examples of some scenarios for applying recurrent neural networks. So consider the following scenarios and answer if a feed-forward neural network or a recurrent neural network would work better given the input and output. Select the arrow next to the question to reveal the answer. So I'll go through, well, first we'll go through the first one. Think about what the answer might be. So the input would be a table of a stock's price each day over the course of 10 years. So the output is, what is the price of that stock 1 week from now? So just one time, 1 week from now. Well, the neural network here that we would use is a recurrent neural network. So this neural network considers a series of data points. This is specifically an example of a time series. Time series data is a sequence of measurements in of a single entity over a period of time for a set interval. The input does not only contain a single data point of the stock price a day ago, but it considers the stock price in the context of the stock prices over the last 10 years. So based on past trends specific to the stock, alongside the hidden layers, weights, and biases, it makes a prediction. So you'll notice that this this RNN, sorry, I just lost my train of thought. Okay. So this this data contains isn't just looking at the stock price a day ago, because if this it doesn't care what the stock price was 1 week ago or even 10 years ago or 1 day ago. It needs to know what it needs to be able to recognize patterns, and patterns involve multiple data points. So recognizing patterns in data requires a recurrent neural network. Next example, input hours studied and hours slept before an exam, and the output is the predicted grade on the exam. So what neural network would work best for this scenario? So in this case, it would be a feed-forward neural network. This neural network would only need to predict the grade on the exam based on a single pair of numbers. In other words, it does not consider the hours slept in studies in the week leading up to the exam, even if you think it maybe should, but it only considers the hours slept and studied during the 24 hours prior to the exam. All right, now right here we have our input, which is a single sentence. The output is the sentiment of the sentence, or what was intended by it. So maybe it's negative or positive or something along those lines. So in this case, an RNN would work. And even though this network only takes a single sentence as input, it would give inaccurate results to analyze the sentence as a whole. Instead, it must analyze each word in the context. Notice that word, in the context of the entire sentence. So whenever it's contextual, it needs a recurrent neural network. And rather than interpreting it as one big input, it is interpreted as a series of words, just like a time series or sequential data. Our last example, we have an input of set of text spanning multiple characters, and our output is what we predict the next word or characters will be. So what neural network would work best in this scenario? A feed-forward neural network or a recurrent neural network? In this case, a recurrent neural network would also work. This neural network would need to predict the next words in the sentence based on the context of the sentence. Contextual prediction requires the short-term memory available within an RNN, or the vocab that we used earlier was long-term short memory, long short-term memory, or LSTM. And normally when you're using an RNN, you'll see this later, but normally when you're using any RNN, it just generates one data point, and then it generates the next data point, and then the next data point. Or with it doesn't just generate, like you can't give it a sentence and then have it generate a whole another sentence as the next sentence. It comes up and it predicts the next character in a sentence. That's what it does in this case. So in order to generate a paragraph, well, in order to do that, you need to have it generate one character, then take what it's generated so far, feed it into it as input, and then have it generate the next character, and then take what it's generated and feed it in again. And then it generates the next character. And you keep on doing that. And with that, it's able to generate an entire paragraph by taking its input that it already had, and then adding more to it. So it just adds one by one by one by one. And if you've used something like ChatGPT before, you'll notice that that each character appears one by one, and that's kind of what's happening behind the scenes. It's generating one character at a time. It's just like if your phone's auto completion, you were able to, if you just opened up your phone's keyboard and it predicts the next word, as you can see on the top, and you just click that a bunch of times, basically. I guess that'd be a simple way of thinking about it. It's like, in that case, it would be with words, but in other cases, in other situations, it would be with, in this situation, it would be with characters. All right, so the first thing that we are going to do is we're going to do this in a project. So we're going to import TensorFlow and other important libraries that we'll be using. So we're going to click run on this code cell and import those. It'll connect to a runtime, and then once it's connected, it'll run. All right. Next, we are going to download the Shakespeare dataset. So you can change this line of code if you wanted to use your own text file. And in our case, we are going to download the Shakespeare dataset as shakespeare.txt, which includes the scripts for many of Shakespeare's works, including Romeo and Juliet. So this chatbot, this text generation RNN specifically is going to generate text, and it's probably going to sound a lot like Shakespeare because we're using a Shakespeare data set. If you got a long compilation of customer service conversations and uploaded it instead, it would probably sound like a customer service chatbot. So you can really change this to do whatever you want. And I know that that ChatGPT was trained on lots of things: Wikipedia articles, Reddit posts, and comment sections, and really anything that had really easy methods of gathering tons and tons of data. This one's going to be a little bit more narrowed down because it's a smaller data set than the one used for ChatGPT. And it's not going to be as well-rounded. It's not going to be, it's going to sound very specifically like Shakespeare. So you're not going to be able to get it to talk how you want to. So yeah. So the next thing that we're going to do is set our training constants. So the following array contains text that already exists for verbatim within the text file supplied above. So text is randomly selected from this array to populate a TensorFlow constant tensor for training, which we will do later. So so I added this so that it's easier for you if you do change your file, because otherwise we would have to go throughout our code and change our training constants in a lot of different areas. Like we would have to replace Romeo colon with a lot in a lot of different places if you change your data set. So if you change it to a customer support conversation, you might see something like something that says support representative or something. And then you would fill that in here as your training constant. So it's just a little bit easier. So first we look at the text. So we're going to read this file in binary format. And the length of this text is the number of characters inside of it. So we can actually see the size of this data set right here. First, I should run these cells, though. Make sure that you run these cells. All right, so you can see right here, it contains 1,115,394 characters. Now, I know I said earlier that this is a pretty small data set, and it is, even though that seems like a very big amount of, very large amount of data for a chatbot or any natural language processing model. It needs a lot of data. So this will still work perfectly fine. It's just that that other larger models that are used for more purposes than just sounding like a Shakespeare play are going to need more data than that. So we're just going to take a sample of the data. This is not essential to your neural network, but let's just take a look inside and see what's here. So we can see the first 250 characters are a script from Shakespeare. So right here, we're going to get the unique characters inside a file. We create a set, which is a feature in a lot of different programming languages, where you take a lot of data. So in this case, it's in this case, we have a string. And Python, if you pass that into the set, it interprets it as basically a list or an array, and it converts that into a set. And a set is a list of unique elements. And then it sorts that set. So we end up with only unique characters. So a set cannot have any duplicates. It's just a list without duplicates. And then we sort that set. And then we print out the number of unique characters. So in this data set, we have 65 unique characters. All right, next we process the text. And also mentioning the 65 unique characters, that includes things with accents. So if there's any character with an accent, that would count as a different character. Which makes sense because the neural network would need to be able to distinguish between if it wanted to, like if it was speaking in a different language, it would need to be able to distinguish between if it wants to put an accent over a character or it does not want to, or what kind of accent it wants to put over it. So next, we're going to process the text. So the first thing that we do is vectorize the text, which is converting it into basically numbers, because that is necessary for a neural network to be able to process it, because neural networks are sets of weights and biases and numbers and manipulating those numbers. And we can't just pass in other things besides that. So yeah, as I said, neural networks work with numbers. All digital or not analog data it can and is represented by numbers on computers. So we're doing that here, and before training you need to convert the strings into a numerical representation. So we're going to use this built-in feature into TensorFlow, which you've probably used before, if you've used TensorFlow, is tf.keras.layers, and we're going to use the string lookup layer, which can convert each character into a unique ID. So into a numeric ID. So it just needs to have the text split into tokens first. So right here we have an example. This is not used for our neural network necessarily. We're not actually using what we're about to create here. We're not using chars in our neural network, but this is just an example to show you what that's doing when we split this apart. So let's see what this does. All right, so we have a ragged tensor because, as you can see, these elements have different amounts. So we have one with one list that is, or one array element that is a little bit larger than the other. And for this basically two-dimensional tensor to be able to work, it needs to be ragged. So it has different amounts in each index, different amounts of elements in each array and each index. So now we're going to create the string lookup layer to reference all the possible words, or sorry, I should have said characters, not words, to reference all the possible characters with tokens. So we are doing IDs from characters. So this is basically equal to our layer, so we can reference this layer that we created later on. But this basically gets the converts characters. When we pass characters into here, it'll convert those into those numerical representations that we were talking about earlier. And then we have we set our vocabulary, which is just all of the unique characters. Remember, that's just a list. And we convert it back into a list because earlier it was a set. So we're converting it back into a list. And then we convert the characters into numerical representations based on the UTF-8 encoding standard. So as you know, each character is assigned a number, and these are those numbers. So you can see it goes all the way up to 65 for Z. Okay, so since the goal of this tutorial is to generate text, it will also be important to invert this representation and recover human readable strings from it in the final layer of our network, because we don't just want our AI or someone chatting with it to input text and then the AI throws back a bunch of numbers and they have to by hand look at a UTF-8 table and think about, okay, 65, that's C, 40, that's A. Like they shouldn't have to do that. So we convert those back into our characters by doing characters from IDs, which looks very similar to the one that we made earlier, the function that we made earlier, except we pass in the parameter invert equals true, and we run IDs, ID from characters dot get vocabulary. Okay, so we could just do list vocab right here from line 2, and we could put that right here. But we don't want to have to convert a set back into a list all over again. So we are we're taking our IDs from characters, we're taking our vocabulary that we got earlier and converting that back into and passing that into our characters from IDs. So let's run this. And it creates a ragged tensor of characters. So there we go. We got our characters back. And we can convert and we can combine this tensor so that now we have like a normal string, I guess. So right there, we have that, and then we can get the text from, so this is basically taking this thing that we just saw on line 1 and taking this and we can run this function anytime in our code later. So we can just pass in whatever we get as the output from IDs from characters or the output of our neural network, pass it into text from IDs, and this will send back this output that we see on line 1, this array of text right there. Okay. So the prediction task, given a character or sequence of characters, what is the most probable next character? This is the task that you're training the model to perform. The input to the model will be a sequence of characters, and you train the model to predict the output, the following character at each time step. And each time step was up here. You see this red, each of these are a time step. And T represents time, right? T, we have HT minus, I'm waiting for it to pop up. HT minus 2, minus 1, and then we have plus 1, plus 2. All right, let me get back here. So recall the long short-term memory of RNNs. Since RNNs maintain an eternal state that depends on the previous scene elements, their goal is to answer this question. Given the characters predicted or provided until this moment, what is the next character? So we create training examples and targets. And this is how we're training it. So we already know what the next text is going to be. We can just grab text from our text file using those training constants. So we search for those training constants, find whatever is after that training constant, and we know what the neural network is supposed to guess. All right, and then we tell the neural network to go ahead and try guessing, and then we tell it how close it was. So guesses the next character, we tell it that it's wrong. This is using reinforcement learning. So this is a supervised network. We're telling it either it was right or wrong, and this is the output that it should have had or should not have had. And I'm getting warned of this meeting ending soon, so we might need to create another meeting. Hold on one second. I'm just going to create another Zoom meeting and send it in the chat. I did not realize it would end so soon. All right, I'm going to send this in the chat and we're going to join this next meeting. So make sure that you don't leave quite yet. Take this link in the chat and open that, and I will open that as well. All right. Let me just save this recording. Hold on.